OK, so we can start if you're all willing to hear about monads. If I were you, I would get out or something like that. So you know what the talk is. First, a small note, who am I and why am I talking here? I've been KD developer for a decade. KD, for people who are not aware, is probably the largest C++ free software project in the world. Both number of lines of code and obviously people who are working on it. The second thing, I'm teaching and I give talks from time to time, and I love functional programming. So because Scott started with my favorite place in whole Berlin, I had to put a picture as well. Again, if anybody missed to visit the Treptow Park, you should go. It's just four S-Bahn stations away from here. But it's not the only Soviet memorial in Berlin. There is one not that big. It is older. It's much smaller. But the great thing about this one is it's in West Berlin. So you have a communist monument in West Berlin, and you actually had Western military guarding the monument from vandals so that nobody destroyed it. And why is this relevant to my talk? It's really artificial. The connection is artificial. I just wanted to show a couple of pictures. The idea is we are one group of programmers, you're object-oriented or whatever, and functional people are usually, at least from our point of view, are a sect, and nobody wants to mix with those guys. And it's vice versa. If you try to talk to a long-time Haskell developer, and you say, oh, C++ is much better, you will be the secty one in that conversation. So this is kind of the point. We are going to mix the Eastern civilization with the Western. So we are going to talk about something that is essentially comes from mathematics and functional programming, but applied to the things that we love in C++. OK, first, a couple of disclaimers. My favorite quote from Phil Wadla, one of the functional guys, you should always write readable code, blah, blah, blah. That doesn't mean that you should actually cater to developers who don't know C++. For example, I've heard a lot of complaints about the things that I'm going to show under the assumption, OK, people will not understand your code. If they don't understand my code, they should learn it. And they shouldn't just, OK, I'm not going to use classes because they are new. The language cannot evolve if we don't use new stuff. The second disclaimer is that most of the presentation, I've shortened everything. So it's not const something reference something. I just put the type so that it fits the slides better. Again, std namespace is omitted and stuff like that. And the third disclaimer, for which I don't have a slide, I don't want to be a functional purist here. So if any Haskell developer is in the room, just from time to time, close your eyes and put fingers in your ears. OK, so we are going to start with what is a monad, then some examples and how you can use monads in asynchronous programming environments. The problem with the monads is that, at least in Haskell community, as soon as you actually learn what a monad is, you need to write a tutorial. And not any kind of tutorial. It needs to be in the form monads are like, and then put a random word like burritos. And it will be really, really, really famous. And this is a graph of registered monad tutorials on haskell.org. Obviously, those are not the only ones. So I will try not to be a monads are like guy. I'm going to try the different approach and to little bit bore you with mathematics, and for one slide only, and then examples, examples, examples. If you get what a monad is afterwards, great. If you don't, then read monads are like burritos. OK. So how did monads come to life in practice in Haskell? Because, OK, this is one of great quotes. If you haven't read James Irie's History of Programming Languages, you should. This is not really a quote of Phil Wadler, but he attributed it to him. It's a shortened version of something that you can actually find in a mathematics book, and that you should not even read and don't understand a word of it. So what's the idea of a monad? Because in Haskell, every function is pure. What a pure function means is it's either a function without side effects, or it's a function that, when invoked with same set of arguments, it always returns the same value. So something that we would in mathematics call really a function. And the problem with the pure languages is that how can you define a function like readLine or something that returns a random number? Because in this case, if this were Haskell, both readlines, because they're the same function with the same arguments or without arguments, they need to return the same value. So instead of having normal functions, Haskell people started using monads. And what is a monad? I still am not going to answer that. But at first, you can think of it like it's not a function that returns just a value. It also returns a function that can return the next value with another function that can return a next value, another function that can return a next value. So something like we have for Std getLine, with the difference that Std getLine changes the argument that you have passed to it. So Std getLine in a perfect pure world would return the stream. It returns the line through the out argument, but it should not change the original stream. It should not take the reference of the original stream here. So this is a Haskell syntax to define a type for monads. Again, don't try particularly hard to understand what it says. It's, in essence, a monad is a structure or something like that with two methods. The first method, the greater than equals, is called bind. And the second one is called return. The return one, and you have a few rules because this is mathematics, and everything that you define needs to have additional rules. We are going to switch to C++ version of the previous. Return function is just a constructor. So you put a value and tell the programming language to put it in a monad, whichever monad it is. Just think of a container or something like that. Bind, on the other hand, is a function that gets the monad and gets a function which will be applied to all members of that monad. And something like Std transform, but a little bit more complicated than that. We will see it later. So the idea is you apply a function to each of the elements. You get a bunch of monads, and then you merge them together into one. And then you get the result, a single monad of the type 2. OK. Let's start with examples. First, before we actually talk about lists, who can say what is the essential difference between these two calls? And not counting, I don't know, moving references or anything like that. What's the real difference, not implementation-wise or not low-level, but really high-level difference? OK, that's also low-level. I'm not going to answer this yet, just in the end. But just remember the for each algorithm and the range for above it. OK, so just imagine a method like this. It takes a list of persons, filters it, gets just females, then gets children of those females, then gets children which are young, and it has a count and offset like we usually do. And the method is not really readable. I guess you all agree, and it's not even complete. You need to count, you need to optimize it so that you don't calculate more than you need to and stuff like that. And the problem is that if somebody changes the API and, let's say, removes the int count, you actually need to go through all of the, through the body of the function and change at least 5 or 6 lines. And that's a big problem. This code is not composable. Not a single part of this code is composable. And monads are here to kind of fix it. So for the list, the two methods that we saw, the return just returns a list with a value that you have passed to it. The bind function does, OK, let's try to use the mouse pointer as Scott suggested. But you don't see my mouse pointer. OK, so what does the bind do? It first transforms each element of your original list. The transform will return a list, well, because a function returns a list, so this will return a list of t. And afterwards, we accumulate all of it, so concatenate all the lists, and we get one single list with all the blah, blah, blah elements that we generated. And these are the two basic methods that every monad has. A list can have, obviously, additional ones, but some of the additional ones which are really useful can be defined in terms of return and in terms of bind. So you can have the normal transform, as we have it in C++ and STL and Boost. You can have a filter function which checks whether a predicate is true for each element and just keep the elements for which the predicate was true. The flatten create a list of lists, and take and drop is offset and count. So once you define this, and we have it in Boost Range library and hopefully in C++ 17, thanks to Eric Niebler, you get ranges. Alexandrescu talked about ranges, Chandler Carruth also, and a lot of people think that this is a useful concept, although it's not the usual code that you would normally write in C++. So the same method that we already saw, in terms of ranges and monads, can be just filter people with a functor is female, then transform to get the children. It's a list of lists. Accumulate to get list of children and not list of children, and things like that. When you remove the offset, you just need to remove one line of your code. It is really composable. It is really easy to read. If anybody has any experience with SQL, this is what the SQL is based on. So if we get the unified call syntax and the call syntax proposals in, then this can become even nicer to write object-oriented dot something style. So you could write the same method with dot filtered dot something. OK, so this was a list. And list is a very useful structure in all programming languages. And when I say list, I think also vectors and everything else that is essentially a range. One of the classes that is also useful is the maybe monad or boost optional or future std optional. The class that is kind of like a list, but with at most one element. So if you have a method that returns, let's go to the next slide. So you have a configuration parsing library. and then you want to read a config value of something. Sometimes that value is just not present in the configuration file. What should your program return? It can't return always a string, because you will never be able to tell whether it's an empty string for a reason or it's just an empty string because there is no key present. The same goes for when a function is not defined, or, for example, square root is not defined on negative numbers. What should square root return if you pass it -2? And obviously, you can have optional values in the arguments and stuff like things like those. One of the solutions to this, for example, for the config, OK, you pass the default config value, and it's usually in all the configuration parsing libraries that I've seen, it's like this. The second option is to use std pair with the first part of the tuple being a double or a result, and the second part, is it really a result or not, which is kind of ugly. The third part is optional argument. Let's pass it as a pointer, which is one of my favorites because we are using pointers for 10 different, semantically 10 different things. And obviously, in the end, we can throw an error or something like that. If we add boost optional or std optional, this becomes more clear to read, and you actually know if it says optional string, it's an optional string. It's not a pointer to a first element of an array of strings or anything similar. And how would you use boost optional or whatever? You can create, again, a little bit bigger method. So config value, as we saw earlier, returns an optional. Then you can check it, is it a valid? So exclamation mark, config limit, blah, blah, blah. If it is, exit from my method. And the same for all the below stuff. So we have at least 2 methods here that return an optional. If we define, again, return is trivial, bind, you can define if optional is valid, then return f of its value. Otherwise, return empty optional. If you switch to, again, range-based syntax, although an optional is, I don't know whether the standardization committee will pronounce it to be a range, you can get to something like this. The method that we saw is, at least for me, much more readable like this. You get a config value. You push it to the method called parseInt. From now on, you are dealing with optional of int. And then you transform it with, I don't know, raise it by 50% and convert it to string and stuff, things like similar things. So, in the end, if there is no value, you can just return the empty string. So, just like for the lists, this makes code much shorter to write, and again, everything is composable. It's easy to change. The third one proposed, the first time I saw this was by Alexandrescu. Essentially, it's the same as an optional, but if it's an empty optional, it provides you with an error message or exception or something like that, not thrown, but actually contained in the object. So you have the optional result, and if, for example, config value doesn't exist, it will return an empty expected and tell you, OK, the exception with this one or the error code is config file doesn't contain something. If there is no config file, you will get another code, error code and similar. So optional is, in functional programming languages, more often used than something like this, because, I don't know, maybe functional programmers don't care about error codes. But for us, again, this would be really nice if it enters the standard. I think that Vicente or something like that has proposed it. I don't know really how to pronounce his name. OK, and the functions that we already saw would look something like this under the N4015 proposal. OK, so we have covered only 3 monads so far, and we should already have some idea of what monad is. If we go to the, sorry, oh, for the love of God. Never try new software when OK. And the same code would be for the expected to be. So you would have the same thing that we used to have in the optional. If an error arrives in any of the bind, transformed, or other methods, it will just be put in your optional. As soon as an error arrives, no other methods will be called. What are the other monads? For example, I/O. We already mentioned that in Haskell, it's a necessity because read line needs to return different values. The same is for parsers. You have a parser and ask it for a token. It will return 1 token and the rest of the parser. So random number generators and others. So what does from our point of view, what's the easiest way to understand monads, at least for me? It's a container object, and you can't access any of its elements directly. You only have the constructor to construct it, and the only way to get an element is to actually tell the container or the monad which function to apply to it. So a bind method can be replaced with these two that are a little bit more sane as far as we are concerned. So you have a map method, which is std transform, and you have the flatten method, which is the accumulate. And the only way to actually get any data from a monad, from any monad, is to pass it a map function. So then, I don't know who talked about std async, so I'm just going to get through it very, very quickly. So you have async, you call something, it returns a future, then you call future.get, and you block your program. And that's one of the main reasons why I really dislike std future, is that in my perfect world, std future.get should either throw if the future is not here, or do something else, but it should never actually block your program. Because std future is kind of designed to work with threads, but just imagine a synchronous operation that lives in the same thread as your code. You call .get, it blocks your code. And the future cannot arrive because your code is blocked. But still, let's say that futures are perfect. And if we are going to the future, pun intended, or use boost thread from version 1.55, you will have a method .den on it. And the method .den is quite similar to some method that we already saw in monads. Do you see which one? It's definitely not the return, so we have a bind. What does a .den do? It accepts a functor, which will be applied to the result, which is essentially what bind does. At least it's close. OK, so how do you define a transform or a map on a future? Quite trivial. You call future.den something. The problem why .den is not really a bind is that the bind should not receive the actual future of t. It should receive just a t. So we need to wrap it just to be able to cast the argument that .den gets and pass it to a function that gets t. OK, so until now, we saw something that everything that is really used in C++ in different projects around the world. But we'll not stop here. There is something that is missing. We have a future. It's like a value in normal world. But in normal world, we also have arrays, lists, and stuff. And we don't have a future that can return us, for example, every second send us something or something like that. And that's called the reactive stream, which became popular again in, for example, in Scala. They use it all the time. The idea is to have a list that is not evaluated immediately, but you can get me the top element. It returns a future. When that future arrives, you can ask for another element. When that future arrives, you can ask for another element. So it's like a collection of futures, and they just fire one after another serially. Examples for something like this can be, I don't know, the user moves a mouse, and you get futures. Mouse was moved to this coordinate. Mouse was moved to that coordinate. Now we are back to our first slide. What's the difference between these two? Can they work on futures? Can range 4 work on a single future?
In the first case, the standard says that begin and end will be called, so you have an iterator range, and then it will take the items from the iterator. But so you cannot change that.
Yeah.
But in the second case, you can make an overload for each, which accepts a future.
Exactly. So the point is that a lot of languages introduced for each Java in I don't know which version. In functional programming languages, those are just functions. So you can create your own algorithms, you can create your own control structures and everything else. For each algorithm, I didn't say it's STD for each. It doesn't care, it just sees what's the argument, uses the ADL, and calls the right for each for that class. So you can create for each that works on futures. And it will just return a future of something and do its job. The same goes for everything else. If we add something to the core language, it usually is not generic. If we add something through generic algorithms, it can be implemented for other stuff as well, and not only for the things that are covered by STL. So our example for mouse movements, in the usual callback scenario, you have a method, you register a callback, and then your method is called every time a user moves the mouse. On the other hand, you can use reactive streams, and it will look something like this if it ever gets implemented. So for each of mouse movements, which are future list or list of futures, and then call on mouse move. This is a little bit shorter, but there is really no point in this code just for the fun of it. The main point is that, again, you can use even reactive streams as if they were ranges. So if you're just interested in mouse movements that are, I don't know, in a scene, then you can transform them to invert the epsilon coordinates. So because windowing coordinates are top left is 0, 0, and in maths, it's bottom left. So you could always do something like this and on the result called the on-mouse move. So you, again, apply transformations. Although you don't really have the data yet, you apply transformations and just don't care about anything else. OK. The problem is that this is not really synchronized all that well. And now we are coming to my favorite type of monad. So we saw the idea behind monads. Those are containers that you can't access their elements apart from calling the bind function or a map or something like that. Continuation monad is essentially future with a .then. You have a process, and that process needs to be able to tell you when it finishes. We can have something quite simple, like, I don't know, algorithm to create an account or log in the user. And when you draw it like this, it's really simple. And you can implement it like get username something, if this, that. It's really trivial, and somebody from, I don't know, high school could do it. The problem is that a lot of these methods are blocking. So get username needs to get a username from the user. So either you block your program, or you switch to asynchronous APIs. Once that you switch to asynchronous APIs, which are usually callbacks in C++, you get something like this. Instead of a normal algorithm, you get a bunch of different separate routines that are not logical parts, that are not logical subroutines of the original program. And instead of the perfect, beautiful diagram that we had, essentially you write this code. And not as pretty as this picture. Usually, you don't really sort the items, get username, on got username, and stuff like that. You just create a soup. This is one of the greatest mathematician artists, George Hart, and his work is called Spaghetti Code. And for some reason, this really represents the inversion of control that accompanies the asynchronous programming. You have the core, which is beautiful, but you never write it, you never see it. You just write the spaghetti around it, which is really neat. So what are the reasons for our computations not to be synchronous? It would be an ideal world if every method could finish in a millisecond. Whatever it does, we wouldn't have any problems with any of the, I wouldn't give a talk today. So you have the user input, you have network actions, inter-process communications, and similar things that you cannot control how fast they will be executed. And then you need to switch to asynchronous APIs. And obviously, each library creates their own wrappers to hide the idea that it's a really simple thing to continue the execution after the previous thing has finished. But since we don't have a normal solution for it, then let's create an object called std thread, an object called qthread, kjob, or whatever, or wrap it in, I don't know, select with a timeout from POSIX and stuff like those. The ideal API, from my point of view, would be something that returns a proper future. Is it a std future? We could debate it, but some kind of future that has a .then method. OK, the problem with the approach that we currently have is that, OK, we decided futures are good, and any class that behaves like a future is a good class. And we could call something like this. You would get a continuation object, or the function that will be called when the future arrives. But the problem is that normal values are not futures. Normal values are by default not monads. So you can't have I, which is an int, I.then, which is not insane. It just sounds stupid. But if you want to actually create generic code you will want to cover normal values as well. And we want to create generic code that will be able to deal with any different kind of futures and non-futures. So we want one code to rule both synchronous and asynchronous world. Instead, in different libraries, bind on a normal value is just calling the function on that value. For std future or boost future, it's .then. And for example, in Qt, if you want to wait for a future to be finished, you need to create a future watcher, then to connect its finished signal with your method that handles the finished signal, which is really beautifully object-oriented, and it sucks. Every time you want to write something that waits for a future, you'll pull your hair if you had left-handed from the last time. So we need to create a method that is able to continue anything that you pass to it. So the first argument here is a future of f, and the second argument is a function that should be called when that's finished. This method needs to work not only on future of t, but also for everything else in the world. And if for convenience, this is definitely not pure way to do it. We want to be able to pass a function that is either expecting future of t, or expected of t, or optional of t, or just just ignore the value. Usually, you need, at least from the theoretical point, you always need to pass exactly a function that gets the value and returns something. We want to create something that is a little bit more convenient to use. OK. And now we are kind of coming to the code that actually looks plausible for a real project. So now it's a forwarding reference, right? The formerly called universal references. But we have a continue video. We get a future. And if, I don't know, if we test whether it's convertible to std function that receives no arguments, it's a nullable function, nullary. And if it's a nullary function, we do the tag dispatch and call the helper function, which will differentiate whether it was a function with an argument or not. But this part is not really that essential. The point is that this is the reason why this library doesn't really exist, because I would need to write at least a few thousands of lines that are just boilerplate to do the static introspection in C++. So there is a demo library, but it's not really fully implemented. OK, so continue with helper. Depending on if it's a nullary type, you just call the continuation without the argument. If it's not a nullary function, you just call the continuation with the value that you got from the future. And this continues for how to implement the same thing for the Q future. Again, this is something that would be in a library, so you wouldn't actually need to write Q object connect and others. And then if you want to cover both boost and std future, you can create something that tests during compilation time whether a specific class has a .then method. If it does, then consider it compatible to std future. But we are going to skip this because it's boring. The next thing is, if we have the asynchronous APIs, we can use it in a beautiful way. You just say get username .then, and then you just nest and nest and nest. And at one point, Herb Sutter called this beautiful because it's localized and it's easy to reason about. But the issue is, whenever you get a more complex algorithm, it's not going to be as pretty as this. You'll have 10 nested calls to .then and others. we want to make it able for us to write actually normal code, and for C++ compiler to know this is asynchronous. It should be, our function should just drop out like, I don't know, like coroutines or something like that. The problem is that we can't really get the syntax that we had in this slide. Oh. I love this program. The good thing is that it shows timing on my screen, and that's the only reason why I use it. But it works so well. OK, so this slide would be the ideal. Unfortunately, C++ is not that willing to give us to overload semicolons and everything else. We need to create some kind of embedded domain-specific language, which can look like this. So you create a serial, you open a block, and then username equals to get username, get password, and others. And the programming language and the library will be able to tell. If get username is an asynchronous method, I'm going to create a continuation for it and execute it when the original method is finished. If it's a synchronous method, again, it will just figure out, OK, this is synchronous. I'm going to execute the next statement immediately afterwards. And how can we do some things like this? Just create serial schedulers. And again, I don't have the time to actually go through the code. And you can create a lot more schedulers than just serial ones. You can mimic every control structure from your programming language. You can mimic if, you can mimic while, any kind of loop. In the same manner, you can create a parallel which will wait for all the subtasks to be finished. You can detach. If you don't care when something is finished, you just detach it. And you can create anything that you actually start to think of. One of my favorites are transactions. You could even create a transactional scheduler which will, if any of the tasks fail, just call all the methods in the opposite order with clean up, clean up, clean up, clean up, clean up. OK. So this is how your program can work. And I have a small and completely daft demo. So we have a window which has a progress bar that just is here to indicate when the program is blocked. If we start some algorithm with synchronous methods, it blocks the whole UI until it finishes. And since my computer is really fast today, this will take a while. And we will have the same thing. When it finishes, it writes out all the text. We want the same thing asynchronously done. And you have, as soon as a message arrives, it is shown to the user, and the program works perfectly, and it's not blocked or anything. The code for it, let me close the window. OK. The code is much prettier than what you just saw. OK, this is the asynchronous implementation. And let's try to find. So both of these implementations are almost line by line the same. You have a little bit different syntax, but you still define your algorithm in the normal iterative way that we all learned in high school. And the compiler does all the magic that it needs to do behind the scenes. So we have a while, we have a nested a block just for the sake of it, and we have serial. Okay, and the next is example that's not really implemented, but it could be implemented like this. You want to create a server, for example, in this case, WebSocket server or whatever, and you have while client equals to something accept. It's, again, a synchronous function. The rest of the code will be executed only afterwards, after the client actually arrives. When you get a client, you detach its processing. And the cool thing about this is that it doesn't need threads to do it. If you use Boost as here, then you'll get even one-threaded server that is easy to implement and works without a glitch. And obviously, if you want to spread to multiple threads, you could, but you don't actually need most of the time. OK. I'm not sure whether I have that much time anymore. The last part is that although this is a nice idea, because it's not supported by the language, it needs to have some boilerplate. So when I write get username, open brackets, close brackets, it doesn't mean that you can't pass it a normal function. You need to pass it a function that returns a function. You need to have actually factories for something. So one of the approaches that you could use is to use Std Bind. And you would say Std Bind some method with arguments that it should accept. It will get you a function that the serial scheduler can execute. Another approach, OK, don't care, done, would be to use something called carrying in a completely wrong way. But carrying is, again, one of the Haskell concepts where instead of having a function that accepts 5 arguments, you have one function that accepts 1 argument and returns a function that accepts 1 argument and returns a function that and 5 times like that. And that's really cool in programming languages that are carry-based. For C++, it's really not. But you can write some wrapper method like called carry, which will create an object, and you can pass it how many arguments you want, and it will return a function. Well, we call it functors, but OK, it will return some functional-like object that the scheduler can call it. Before we get to this part, the benefit of this approach is, OK, you don't need any changes to the language itself. The second benefit is that you can just exchange an asynchronous method with a synchronous one without changing your code, which is useful for testing purposes, for actual program validation, or using Clang Analyzer on your code, because all of those tools just don't work with asynchronous code. In this way, you have the same algorithm that you wrote, and you can run it on a synchronous API or asynchronous APIs. And now we can go to the question section.
I have 2 questions, actually. The first one is connected to what you mentioned in the last slides. Isn't this what the await proposal is trying to get into the language?
That's one of the things that I actually didn't want to mention during the talk, especially because I expected somebody to ask it. It's like the range 4. The await proposal will work only for the things that it is meant to work with. You will not be able to use things like these for other monads. You could easily replace any of the methods with a parser monad, with any monads, with a await proposal you would not be able to. So it will be limited just like range 4 is limited for things that have begin and end.
So we would need something like a do notation in C++ in order to really be as general as we should be.
If they made the await be something that is more generic, then yeah, it would be like a do notation in Haskell.
Okay. And the second question is connected to the to the range-based for example and the for each example. And you can actually define global begin and end functions so that they return the kind of iterator that you want. And
yes, but they can't work on futures. Because when you call the range for, it will immediately be executed. And for the future, you can't execute anything because the future is not here, unless you block and call .get. So here the idea when you create for each for your specific class, it will return a future of something. It will not actually try to iterate through your collection. So that's the main problem I have with range 4 is that it needs to be executed. It's not something that returns a function that can be executed, but it needs to finish iterating over all elements when you have the closing curly brace.
Hi, it's more like a comment than a question. Always about the same thing about the await proposal. I think that the important point when talking about monads here is that if we're going to get the await proposal accepted, I think the committee has to make sure that the semantics is generic enough to be able to use the same syntax also for other kinds of monads. For example, if we can use the await yield syntax to generate a list using the list monadic bind operator instead of doing asynchronous stuff, then we will have the do notation that we see in Haskell.
Okay, I'm truly not optimistic with that the await will ever be anything more than just await for a task. But if it ends up as being something really generic, then I'll be happy. The only disadvantage that I see from the await is that you actually have to write await before something that is asynchronous, and you can't replace it, hot replace it with any other non-asynchronous function. So here I like the idea that you have the same syntax to call both synchronous and asynchronous methods, and for await it's not the case. You need to write await to actually tell the compiler to await something, which is for me weird.
That's only a syntactic detail.
Yeah.
What I mean is that if we can write await something also for a list function that returns a list, and then suddenly we obtain a function that iterates over the list.
You would need to get first the monads proposal written to be able to use the monadic generator. So as far as the monad proposal goes, the guy who is writing the std expected proposal, he started writing the monad one, and he got one reply on the std proposals mailing list. The reply was from me. I was saying, okay, kudos for starting this, dude, and it just died out. And I tried to pull a couple of people like Bartosz to join the discussion, but it was unsuccessful totally. So if you know anybody who wants to write a monad proposal for the committee and then change Microsoft's view on await, and it could work.
I think that Microsoft is not touched by this because for the asynchronous stuff, the proposal will continue to work in the same way. It's just to make sure that it's generic enough to be used.
I hope so.
As someone who deeply cares about performance, I always wonder regarding the functional style of programming. Don't you have tons of temporaries, and especially if you would like use any kind of lists, wouldn't they be allocated, or is it all functional and not actually proper lists as we are used to, but only like type lists and tuples or stuff like that?
Okay, so here, the only type of lists that are used are compile time lists, so template metaprogramming stuff, which the last time I checked totally unwraps, and essentially I got the same assembly code for the serial schedule or when I create my own callbacks. So if it's implemented carefully, you will not get any overhead compared to the code that you currently write. As for the ranges, I guess you should watch Chandler's talk, which is some, okay, value semantics and range algorithms. So some of the things are designed to be just views on the collection, but some of the things like sorting needs to actually be able to sort. So for a list, it would create a vector, if I remember correctly, and sort it and continue with the other methods. Okay, I have four more minutes.
Have you been able to use any of this stuff in some of the work you're doing in some way?
Okay, the library, this library, no, because it doesn't exist. But the original idea for continuation-based workflow, I actually used it in one of the KDE projects that was deployed with every KDE machine, so not an insignificant user base. So this is really usable. It's not only academic talk or anything, although I can do academic talks as well. So it was in production-ready code for a couple of years. And then I deleted all the code that was asynchronous, but that's another story. Okay, thank you.